So we looked at three different aspects so far. One was related to computation, then memory, then synchronization. What we are going to look at are some of the different topics which you might find useful going forward in your work. I'm planning to cover three different topics, but let's see, depending on the amount of time and amount of discussion we have, we may not be able to cover three, but let's see. Okay, the first one is about high-level library programming using functions and thrust. So this is going to be very productive for you guys many times, and therefore I thought that I'll cover this up. So let's do what we mark as functions. I think there is a little bit of noise from somewhere. May I request people to please mute? Yeah, so there are three different types of functions that we know of. One is the device type. Well, we have not really studied that, but you can mark a function to be of type underscore underscore device underscore underscore that gets executed on the device, and it's also callable from another either device function or the kernel, but it is callable from the device. Global, we know, is a kernel which is executed on the device. It is callable primarily from the host, but with dynamic programming, dynamic parallelism, it is also callable. I mean, you can call a kernel from a kernel also, so it is callable from device also. Similarly, there is a host tag, which essentially is our usual function that we specify on the CPU, which is executed on the host as well as callable on the host. Okay. So this basic part is something which we should be aware of as we go along, right? So let me give you one specific example where we have these different kinds of functions defined. And interestingly, the same function can be marked as both host as well as device. Okay, so this dhfun is device host function, okay, which can run on both CPU and GPU. Now this might look very interesting, but we have to be a little careful about what all statements we can push inside such a function. So the kind of statements we are allowed inside the host device functions are the ones which can be executed on both CPU and GPU. Okay. Similarly, if I can have a device function, that is device only function, that can run only on the device, right? We don't have to worry about then what is possible on the host, etc., right, in such a function. So such a function can call a device host function, right? So the device function can call device host function because device host function can run on the device also. Okay. So that part is okay. Global, we know it's a kernel, right, which is anywhere running on the GPU. So it can call a device function. It can also call dhfun as such. Okay. What about this line? Right, so I'm talking about this line. In what kind of functions you will be able to use such a line? That is unsigned ID equal to block IDX dot X, etc. Can somebody tell me what kind of functions will be able to use this particular line? One answer is given, right? So the underscore underscore global underscore underscore, that is kernels, we'll be able to use this. That we also know. Okay. Hari says that in device functions we'll be able to do. That is in dfun, if I move this particular line, that should work. Okay. Okay, that is correct. How about device host functions? So as far as host functions are concerned, yes, we cannot use these thread IDX, block IDX dot X because those are specific to GPU. So in host functions that is on the CPU, we won't be able to use those. But as far as host device are concerned, we will still be able to not use them, as Harish has rightly pointed out, because the code inside host device functions like dhfun, this should be able to run on both host and device, and therefore block idx.x, thread idx.x are not available in that code. Okay, sounds good. This host function is like any other CPU function, so that is just marked as host. And from there also you can call dh1. So this is a very interesting part, that dh1 I can call from both device as well as host, and that can give us some advantage, some mileage as we go along, we'll see. So this is only part of the code. I'm going to show main now. From main I can call a kernel, right? Ignore that gray part, that is our usual processing. I can call a host function, that is just a CPU only function. I can also call dh1. Can I call dfun from here? Can I call dfun from main? That is device function from main. Okay, Shiva says no. Right, so the device function is callable only from the device. Right, only the kernel is callable from the host. Okay. All right, so this part seems to be fine. I'm going to show it pictorially now with respect to the functions that we had. So we have this upper part as the CPU and the lower part as the GPU, the greenish one. The kernel and dfun, that is the device fun, are running on the GPU, and dh1 is a mix of host and device. And then there are these arrows which convey which functions are calling which functions. Right? Some of the functions, some of the arrows are missing in this. Right? So in general, not specifically in this particular program, so those arrows are present, but there are some other arrows which are possible. If I'm talking about, let's say, a host function or a kernel or a device function, can somebody tell me which other arrows might be possible in this diagram? Host fun can call dkernel. Very good. Right? So from host fun also I can call a dkernel. That is very correct. Right? As Harish has pointed out. Any other arrows possible? Dkernel to dh1. Right? So can I call directly from dkernel to dh1? Yes, that is possible. Correct. Any other? As Lakia has said, this is correct. What else is possible? Okay, so other things that are possible are essentially self loops, right? So I can call dkernel from dkernel. Can I call dkernel from dfun? Can I call dkernel from dfun? Sandeep says yes. Are there people in support of Sandeep? Okay, so yes, it is possible. Sandeep is correct that you can call dkernel from dfun. How about dkernel from dh1? The opposite of what Elakia had said. Right? Can we call a dkernel from dh1? Okay, Sandeep says yes, Siva says yes. Any other suggestions? Okay. Shrikant Prasad also says yes. So yes, you're right. Because kernel can be called from main also, and we just said that it can be called from dfun also. That means that it is callable from both host and device, and therefore it should be possible to be called from dh1. Right? So that is good. All right. So those are the other arrows which are possible in. How about dh1 to dfun? Harish says not possible. Sandeep says yes. Okay, so now we have some interesting discussion. Okay. Okay, so we have two parties, Harish's party and Sandeep's party. You want to join which one? Okay, Shiva says it's possible. Sandeep is trying to convince people to join his group. Srikanth says yes. Okay, so only Harish is saying that it's not possible. Okay, let's understand what is happening. Right? So definitely from a device function, that is dh1, you can call dfun. So that part is okay. From device, you can call dfun. Can you call dfun from a host function? Something similar to this. You can call a kernel from a host function, but you cannot call a dfun from host fun, and therefore from dhfun you cannot call dfun. Okay, so Harish turned out to be right in this case, that you cannot call a device only function from a dh1. It's possible to be called from a device function, but not from the host, and therefore, so in some sense, whatever is possible in dh1 should be an intersection of whatever is possible on device as well as on the host. Right? So from device it is possible, host not possible, so overall it is not possible. Okay, is this okay? Any questions, any concerns here? Okay, good. Okay, so let's move ahead. Okay, so let me talk about a little bit about what is meant by some memory which is going to be accessible from both CPU and GPU. Right? So far we have said that for for discrete GPUs, that is the usual GPU that we have on our machines, the GPU memory is separate, CPU memory is separate. So that part is okay. But there is some small technology which GPU provides, using which you can declare a variable or create a variable once, and that is going to be accessible from both CPU side as well as the GPU side. Now, if that is the case, why didn't you teach us earlier? Life would have been much more easier, right? So yes, that is true, but it also has a performance penalty associated with it, because that is not something which is directly supported, because CPU memory and GPU memory are actually separate. So we have to transfer it via the PCI Express bus, which is relatively slow. So just that, in case of this memory that we are going to talk about, the way of creating these variables, this transfer is going to be handled automatically. You don't have to invoke CUDA mem. Okay? And as soon as it is handled automatically, it might not be optimal. For example, if I am writing to a variable and now the hardware sees that, oh, this memory location is modified, let me transfer it to the other device. But that might not be optimal way, because you are writing to one memory location and then you will write a few more memory locations, and then programmer feels that now it should be transferred because now it will get used on the GPU or the other device, right? So the other way also is possible, from GPU to CPU. So therefore, programmer is the best judge of when the memory transfer should happen, and therefore it's not always possible that this memory will be optimally kind of transferred across the two devices. But let's understand what that means. Okay, so these host device functions that I was talking about, since these functions are going to be possible to be run on both CPU and GPU, ideally they should be using a memory which is accessible from both the sides. If I am using only the CUDA memory, I cannot use a host function for that. If I am using CUDA memory, I cannot use a host function for that. If I am using a regular global variable, I cannot use a device function for that. So I need some memory which is going to be accessible from both the ends, and that is called as HostAlloc'ed memory. Okay? So how do we create a HostAlloc'ed memory? Instead of using CUDA malloc, just use CUDA HostAlloc. That's it. And you specify the syntax in a similar manner, that ampersand of counter, which is declared as in this case int star, declare or essentially create a memory of that much type. These are some flags which you can mark as 0. So I create that much memory. So now counter is a variable on the CPU which is pointing to a memory which is created in some sense between CPU and GPU, right? So, or on both CPU and GPU. I can access that directly on the CPU. So when I say star counter equal to 0, I'm actually dereferencing the counter and I'm saying that its value should be 0, and in main I can just access it like any other variable, right? Like any other pointer. I can also pass that parameter to a kernel, and inside the kernel I can call a device function or directly access that counter as a pointer, right? As if that variable is present on the GPU. But the variable is going to be present only in one location as such, right? So it's just that what is going to happen is that there will be one memory location specified on the CPU side, CPU memory, another location correspondingly on the GPU side, and this memory transfer is going to be transparently handled underneath by the CUDA runtime, right? So that is what is essentially happening here. So what will be the output of this program? Can somebody tell me? So there is no compile time error, there is no runtime error, and the code actually works. Although there is a single counter, single counter which is allocated using HostAlloc, so you can access it from both CPU and GPU side, right? And therefore, you'll also be able to access it from the host device function. So the HostAlloc'ed memory is going to be your friend when you are dealing with host device functions. Okay, so I didn't see any responses. So here it's going to print main as 0, then print k counter, which is going to call fun counter. There it is going to get incremented. Can you call fun from kernel? Yes, because it's a device function also. That counter is going to get incremented to 1. So print k after fun is going to write 1. After that, the host waits. Then the host calls fun because it's a host device function. It again does plus plus star counter, so it becomes 2, and main after fun is going to print 2. Okay. Any questions on this? Okay. So because there is some memory copy involved, plus the way it gets implemented, this particular HostAlloc'ed memory, is that a page is going to get pinned into CPU memory. Pinned meaning that page doesn't get swapped to the hard disk, right? So we have this virtual memory in the operating system. We can create a process which is larger than the memory size, right? So that is possible because only the required pages are brought into memory. Other pages might be there on the disk. And then whenever you require, you can load some other page which is required and move some other page which is not in use to the hard disk and so on. So all of this is called as paging. So when you pin a particular page, that page does not get swapped to the hard disk, right? So that is some technology which NVIDIA uses for allocating HostAlloc'ed memory, HostAlloc'ed variables. So that memory remains pinned, that is memory remains in the operating system, let's say accessible pages, and that gets transferred to the GPU memory using the driver. Whenever we use this pinned memory, the performance of the operating system reduces beyond a point because now you are interfering with the operating system page scheduling mechanism. Right? As you increase the number of such pages which are pinned, the amount of memory that is available for the operating system to swap, etc., that reduces, and therefore the overall performance of the system might go down. Therefore, it is recommended by the operating systems that you should not have too many pinned pages, and therefore it's recommended that you should not have too much HostAlloc'ed memory. For example, you should not use HostAlloc'ed memory to put all your data. If you have some sort of a metadata or very small amount of data which you want to transfer automatically across the two, then you should use the HostAlloc'ed memory. If you have the actual data, which might be in millions of data points, then you should use CUDA malloc. Okay, so we discussed about the output of this. Can Can we, okay, there is a question. Could you please explain why pages need to be pinned for host or that is the technology that they use. If it gets swapped, then there is no page that is going to be accessible for doing this automatic data transfer. So that is how NVIDIA has implemented it. And that is the reason why we require. Otherwise, the page will get swapped, and when the driver is trying to copy, the page is not available. So it might actually get into probably a page fault, which will take a large amount of time because handling the pages, bringing it back from the hard disk is slow. So that interference will require NVIDIA to probably change some processing inside the operating system. So to avoid that, it is using this pin. Okay, so what we are going to do now is to look at slightly modified code. The main remains almost the same. The kernel also remains the same. Right? So the main and the kernel remain the same as were before. So we have this CUDA HostAlloc'ed Memory, etc. Fun, which was the host device function, also remains almost the same, except that I am adding this sync threads there. Can you tell me what will be the output of this program? Okay, no one? Okay, Harish is asking, will this compile? Good question. Any other suggestions? So Harish, why will this not compile?
So the C threads should not be used for a host function, right?
Right. So that is correct, right? That's the right observation. We said that host device should be intersection of what is possible on CPU and GPU. Sync threads is possible only on the GPU. You cannot use it in main, for example. So therefore, you should not use sync threads there. So it's not available on the CPU, and therefore it's a compile time error. Okay, so I'm going to change it a little bit with CPU only memory. What I'm going to do is, instead of CUDA HostAlloc, I'm going to use CUDA. Okay. And then do print k here, and then call fun. So that part remains the same. Right? I have removed that sync threads because that doesn't compile. Now can you tell me, will this code compile, and what will be the output? This is primarily to understand, to make sure that we understand things. That's why I'm showing these variants. Because sometimes we can commit mistakes. Okay, so I don't see any reactions. Sorry, somebody wanted to say something. Sandeep says now it compiles. Sure. Any other suggestions? Hari says cannot access counter in main function. Sandeep says 2. Okay. Okay. Any other reactions?
Sir, counter memory allocation has happened in GPU only. So host could not access that memory.
Okay.
It can access, no? It can access since the counter is defined as a int in the main function. So I think it can access.
Okay. All right. So that seems to be a good discussion. So whatever we have done so far, CUDA malloc, right? We said that this counter is on the CPU, but what it points to is on the GPU. And that address is not, or often not, valid on the CPU side, and therefore we can access counter on the CPU, but we cannot access star counter on the CPU. Right? And therefore this is going to cause an issue with respect to that the counter, I mean essentially dereferencing of the counter is not allowed in the CPU memory. So CUDA malloc memory has to be passed as a parameter to the kernel, so that it is accessed directly in the GPU. but we should not access it on the CPU. Star counter. Counter you can change. So for example, I can say counter equal to malloc or counter equal to ampersand of x. That part is okay, but we should not dereference. Okay, Sandeep, is that all right?
Yes, sir. I didn't notice this. Sorry.
Sure, no problem. That's fine. We are all here to
Maybe
learn.
if you put ampersand here, then it will run. I think no.
If we use what?
Instead of dereferencing with the star, like we just put a like ampersand sign here, we'll be able to.
Ampersand counter equal to 0. Is that what you are saying?
Yes, yes. Instead of the star counter.
No. That will not work because ampersand of counter, we cannot change the address of variable.
Yes.
So if we have to make counter as null, then we have to write counter equal to 0. Right? So counter equal to 0 will work, but star counter will not work. Neither in this line nor in this line. Right? So both of these will be wrong. Okay, as well as here.
Printing the address stored on counter is possible in CPU, right?
Yes, that is possible. So you can write printf %d counter. That is okay. So you will get the virtual address of that CUDA malloc memory from the GPU. Correct.
Okay.
Shiva says, can increment happen on host device? Yes. So the usual operators that we have in C, those are supported on both the host code also as well as the device code also. So that part is okay. Right? We can write ++ in the kernel. We can write ++ in main also, and therefore it is possible to be done in host device functions. Any other concerns? All right. So, okay. So I'm going to change the program a little bit. I'm going to make it as a global variable, right? So int counter as a global variable. And now I have slightly changed the program, but more or less it remains the same. Now does the code compile and what is the output? Harish, does the code compile? You have been saying that it doesn't. Okay. Shiva says it doesn't compile. Okay.
It should not compile, sir.
Okay. Harish also agrees with that. Okay. Any other suggestions? Okay. Why will it not compile? Okay. Lakia says whether the global is accessible by the device, right? So that is the question. So rest of the code is the same. It's only this counter which we are using inside this, right? So that counter is definitely accessible inside main, but whether it is accessible inside the device here, inside the kernel, as well as inside the host device function, that we don't know. So the global variables are created in the memory of the CPU, and therefore these are not accessible in the device. Global variables are not accessible on the device, and therefore it's not going to be accessible either on the host device function or inside the printk kernel. Okay, so I cannot do that. But sometimes it is very useful to have those global device functions. So can I do that? Well, what I could do is maybe I'll do host device and then use it inside the host device function, as well as I use it inside the kernel, as well as I use it inside main, right? Maybe I should be able to do that. Unfortunately, this also doesn't work because host device is used only for functions. It's not supported for the variables. And therefore we won't be able to use this as well, right? So what is possible is this one. So you can declare a global device function, use it, yeah, so then you can use it inside the device functions. But unfortunately, this ++ counter is going to be accessed from both the CPU as well as GPU, and therefore in general, that plus plus counter will fail when the function is, when this particular host device function is called from main. But in this particular code, we are not calling it, right? So from main, I am just calling print k. Print k is calling this fun, and therefore this particular plus plus counter happens only on the GPU. That the compiler is able to figure out. So it just leaves you with a warning that this counter is not accessible from a host function. But if you actually have a call to fun from here, then the compiler will give an error. Okay. So in general, the device global variables are accessible only from the device code, not from host device or not from host. All right. So that sounds fine. I don't see any questions. Okay. So let's see if you are able to write quickly a CUDA code to increment all the elements in an array, and make sure that this code is callable from the host as well as the device. So please try that out in a few seconds.
Sir, I have a question, sir.
Yeah, go ahead, Sandeep.
Sir, when we declare these device variables like global or something like that, then do we need to transfer this data to the CUDA?
Yes. So we don't need to. That is the good part, that the underscore device underscore variables, which are globally defined, these are directly created on the GPU memory. And
even if it is a dynamic variable, even if it's not constant? Like, let's say, even if I define some malloc, like something, so some pointer to array or something like that, then also no need to transfer to the device?
No. Whatever we are doing with CUDA malloc, that needs to be transferred. Okay. Only these variables. See, these variables are like global variables which are accessible from all the device functions, including the kernel, including if there are only device only functions. All those variables will be able to access that variable. So you modify from one and it will have effect in the other.
So instead of counter, if I define here an array, so then also
you can define an array, and that array will be accessible from all the device functions.
Okay, thank you.
Yeah, so you can modify it directly on the device. If you want that array to be accessible on the CPU, then we need to do CUDA method. We cannot access it from the host. So if you want that array to be accessible from the CPU, then we need to do CUDA method. But if it is like from one function or one kernel to another kernel, then you can just modify it directly, and when you call the next kernel, that modification will be available. Okay.
Got it, sir.
Sure. Okay, Harish has given us some code. Sure. And how will you call this DH1 from the GPU, Harish, or anybody else? So what Harish has written is that there is a loop using which we are able to increment this ARR of I, and this DH1 can be called directly from the CPU using the array. Right? That array should be available on the CPU. Now, in a similar manner, I can call it from a kernel or a device function, the DH1, with array as a parameter, which is a CUDA malloc memory or the global device variable. So I can possibly call it that way, but there is something slightly more that is required on the GPU side. Right? So on the GPU side, we require that this is getting called from a sequential kernel. That is a single threaded kernel, right? Because we already have this loop inside that. Now the question I have is that our CPU is, let's say, sequential. I don't have, let's say, parallelism, OpenMP parallelism or other parallelism on the CPU side. On the GPU side, I do have parallelism. I can increment all these variables in parallel, all these memory locations, array elements in parallel. Is it possible for me to write a host device function such that when I call it from the host, it runs sequentially? But when I call it from the device, from a kernel, then it becomes parallel. Can somebody think of modifying this code such that it becomes sequential from the CPU, same code, same host device function, sequential from the CPU, but parallel on the GPU? I hope the question is clear. If it's not clear, please let me know. I think if you look at what Harish has written, I think then the concept will be clear that we have this loop which is going to be sequentially executed by each thread, whether from the CPU side or from GPU side. From CPU side, we are okay with that, but from GPU side, we would like to avoid that sequentiality. So I can write two different functions. One I call from CPU sequential, another I call from the GPU parallel. But then can I now use host device? I have just a single copy of DH1, and still its behavior is different on CPU and GPU. Okay, Harish says caller equals CPU, then for loop as caller equals GPU plus ARR. Sure, that's a good way of doing it. Sure. So I have also written the code which is similar to what Harish had shown. So we have some sort of initialization here, and I do a CUDA mem copy from CPU to GPU, and then call this fun with ARR. Right? So this fun is the host device function, and therefore it has a for loop similar to what Harish had written. Alternatively, I can call a dfun kernel with one thread, which is going to call this fun from the device, and that will again run it from 0 to n. Here we will assume that n is hash defined. So therefore, it is accessible on both CPU and GPU. So that part is okay, and this works fine. Hari said that you can pass it as a parameter whether you are on the which device you are on, CPU or GPU, and depending upon that you can take a call. But is there any other way in which we can do that? Okay, so there's a host-centric part because this is sequential on the GPU. Can you avoid the for loop? Well, you might be able to do something like this, where I push the for loop on the CPU and call this fun with a particular ID, particular address. Inside this host device function, I just do ++ of that. So if I call it from the CPU, it becomes sequential anyway. But if I call it from the GPU, which I am now invoking with n threads, each thread is going to call this fun with different IDs or different indices of different memory locations of this array, and therefore this can become now parallel on the GPU. Okay, I hope this point is clear. And here we have not used any specific thing that whether this is running on the CPU or GPU. It just happens, right, based on the address that gets passed. Just that this function gets invoked n number of times on the GPU, whereas it gets invoked only once. Sorry, it gets invoked n number of times on the CPU also because of this loop. It's just that it is called sequentially on the CPU, but in parallel across different threads on the GPU. Okay. Any questions on this one? All right, so I'll move ahead from here. So this is a device-centric code. You can actually do something like you don't have to write the for loop also on the CPU, right? So you can just call fun with some parameters and dfun with some parameters, and you can still get the effect that we were discussing, which I'll leave as a homework exercise for you. Okay, so let's come to thrust. That is thrust, I mean, those of you who are aware of the standard template library on the C++ side, you will see that there is similarity with respect to that in case of thrust. So what we do is that we specify these various aggregate functions or various parallel functions to be done from the CPU, and all of that internally, how the kernel should be launched, how much should be the parallelism, etc. All of that gets handled internally by this library. Right? So you will see that it's very productive to make use of thrust. So those of you who are actually dealing with GPU based programming, I strongly recommend using thrust or the next version, which is called cub, to be used in your codes. Your code size considerably reduces. You are relieved of a lot of processing that needs to be done. Plus, these thrust functions are very nicely optimized, and therefore you will get good performance. There are some cases where you should not use thrust, where you have to write your own code, but those cases are few in number. So I strongly recommend, if you want to make use of it, use it liberally in your code. Right? So it supports some sort of a vector. It also supports set, but that is not something which gets often used. And the programmer, once you define what the type of the variable is, you don't have to care about where it is running, whether it is running on CPU or GPU. It can run either way. And it does use functors, which I'll explain what those are from C++ side, and also host device functions. So that is the reason why we studied those. So let's understand that. So with a good chance, thrust is likely to be installed already in your CUDA setup. So thrust / host _ vector, thrust / device vector.h, these you can include. IOStream is a C++ library. So far whatever we were doing was C specific. Now we are getting a little bit of object oriented part, and therefore I am using the C++ style functions. But if you are not comfortable with C++, feel free to ask me. So this, like we have printf scanf, C++ has C in, C out. So we'll be able to make use of them. Right? So let's declare a vector h which has just 4 integers. Okay? So I can just declare it as thrust : What is thrust : Thrust is a namespace in C++ which has a host vector type, that is a class. Within these angular brackets, I specify a templatized parameter which defines what should be the type of each element inside this host vector. Okay, so host vector of int, host vector of char, host vector of double, host vector of your own type, some user defined type. All of these are possible. I declare h as the variable. So think about h as an array of 4 size. But this array is going to be very restrictive. We are going to be able to do more things when you have host vector. Can I individually initialize elements, for example, h of 0, h of 1? Yes, you are able to do that. Right? So host vector is initialized, this variable is created on the CPU because you have marked it as host vector. And you just convert this to device vector and the same code works. And the code works such that everything is happening on the GPU. So all of this h of 0 equal to 14 will happen actually on the GPU if you have this as device underscore vector. Okay. So you can do it in a similar manner. H.size returns the current size, so this gets printed that is going to be of 4 size. And I can also print the content, so I can run a loop which says runs from 0 to h.size -1, and I can print h of I. So all of this works perfectly fine on the CPU anyway. I can resize h on the CPU, and I can do it also on the GPU. So I can just do h.resize, and now the size will say that it is going to be 2 instead of 4. Now I can copy this host vector from CPU to GPU. Right? So in general, we would have used CUDA memcopy. In this case, what you can do is you just declare it as device vector of type integer, as d is the name of the variable, and you just do d equal to h. Right? So I can put a semicolon here, and the next statement could be d equal to h, and it will make sure that CUDA memcopy happens internally, and it copies from host to device appropriately. If you write h equal to d, the copying will happen from GPU to CPU automatically. Okay. So that is the best part about thrust, that a lot of these internal details are kind of handled underneath and you don't have to worry about them. Can I modify the, note that device vectors elements are actually stored on the GPU. So can I modify those on the CPU? Can I do something like d of 0 equal to 99 and d of 1 equal to 88? Yes, you can do that. This is not the best use of parallel processing, but I'm just mentioning this to you that because of the power of operator overloading and C++'s use of that, we are able to get that particular device vector accessible from the host function also. All of this we are doing inside main. Okay. And they automatically get deleted using a destructor at the end of the function. Right? Any questions on this part? I'll show you more examples of thrust, but any questions on this part?
Sir, the whole point of using GPU calculations is just for performance reasons, no? Or else we could have used only C++.
Correct.
So here, like if you use this approach, like host vectors and device vectors, so how does this one is different from normal C++?
Okay, so there are two questions here. I'll answer that. So first thing is, this code is not nicely parallel. We are just talking about 4. We are accessing individual elements, right? So that is not a good, nice parallel code. This is actually sequential code. We should not use GPUs for that. We should use GPUs for this. We should not use GPUs for this. Because there is a CUDA mem copy involved. As soon as you are accessing D of 0, that memory is available on the GPU. So you are going to do a CUDA mem copy on device vector of 0th element and set it to 99, right? So that is not a good idea because that's not a aggregate operation. It's individual elements, but it's just conveying it to you. The second thing is, how is it different from our usual C++? There is a lot of C++ syntax which is underneath this. For example, D of 0 doesn't mean that D is an array. D is not an array. What is D? D is actually an object of type host vector of int or device vector of int. D of 0 is not really accessing the first element of this object because this is an object, this is not an array. So this rectangular brackets is an operator which is overloaded by this class device vector, templatized class. That processing internally accesses this int star array which you have actually created and mallocked when you declared the variable, right? So as soon as we did this, at that time there was a integer array created which is pointing to CUDA malloc memory, and when you are accessing D of 0, it is actually accessing the it's either doing CUDA mem copy or it is calling the kernel using sequential processing such that it is writing that 99 to that memory location, right? So there is a lot of C++ that we are using here which so far we did not use in our earlier 3 classes. Okay. Any further questions on this?
Sir, so is it better to use this thrust device vectors instead of doing CUDA mem copy?
In general, if you have a large amount of processing where you have an array which should go through different kinds of processing, it's a good idea to use thrust. But if there is a processing which requires you to do a large amount of computation directly on one particular element, or where the processing changes from parallel to sequential, then again parallel to sequential and so on, there most of the times a kernel is going to be useful or multiple kernels are going to be useful. Many times what happens when we do CUDA programming is that we declare the CUDA malloc happens once, we transfer the data, then we have large number of different kernels and then we copy the result back and then use it on the CPU or print it. So there we precisely know that the CUDA mem copy is happening only once before the kernels and once after the kernels are over. In case of thrust, because of the abstraction, you might not know where all it is doing CUDA mem copy. That is a little bit of disadvantage. that is a cost which we have to pay for the abstraction. So if you know what is happening underneath, then your performance will still be okay using this. Otherwise, you should be a little careful. Harish has a question. Can we add host vector and device vector directly? Can you add those like, can you do h of I plus d of I? Yes, you can do that. So h of I plus equal to d of I. Yes, you can do that. But once again, I'll tell you that this is not a good, I mean, it's supported. This is not performance friendly because you are accessing each of d of I separately. And that means there are those many CUDA mem copies going to happen. So instead, it is better to do host vector h2 equal to d. That will do a single CUDA mem copy of the whole vector. And then use h of I plus equal to h2 of I. That is better. Where both h and h2 are on the host. All right, so I'll give you some more examples of thrust and you will see some benefits of that. There are other header files which are providing different functionalities like copy and fill, which are typical operations which you will require. Right? So for example, if I want to initialize array 10 of integers, right, to 1, I can just declare that size and the initial value. This is all happening on the device now, right? So all of this, this device vector final memory is going to be on the GPU. First 7 elements to 9, so I can say d dot begin plus 7, right? So these are called as iterators, as we, as some of you will know in C++. So begin and end define the first element and the one element after the last element. Right? So begin plus 7 is going to be the 8th element really. So I specify that from 0 to 7. So there is going to be less than d dot begin plus 7, and therefore the last, the 8th element will not be included. So 0 to 7, 0 to 6 will be included. So, and all of those will be set to 9 using this function called fill inside the thrust namespace. Can I initialize a host vector with the first 5 elements of D, similar to what Harish was asking? A better way to do it is using these iterators where you specify the range and you copy those elements here. Right? It's only the first 5 elements. I can set the elements of h to 0, 1, 2, 3 using some functions in sequence.h. So essentially the function is called sequence. So you can just say h.begin, h.end, and it will start it from 0. Note that in this case, the host size, the host vector size is already known as 5. If you had not initialized it with this, then the host vector size would have been 0. So if I do h.begin and h.end, it will be a 0 element vector which you are copying. Right? So whatever be the size of that D, that gets incremented or changed based on what the number of elements of H are. I can as well print D just using our usual for loop. That is also okay. Any questions on this code? Okay, so yeah, so there are a few aspects that I will mention. For example, I declare a host vector and a device vector. As soon as I do dnums equal to hnums, device vector equal to host vector, it's going to call CUDA mem copy. So you should be aware of that. You see it as a single statement that equal to is actually overloaded for the device vector. When I do initialization, automatically there is resizing happening, right? If required, right? So in this case, it's probably not required, but in general, there might be a resizing happening. So that means there is a CUDA free happening as well as CUDA malloc happening. That can be, I mean, that may not be known to you unless you look at it very carefully. Now that you know about some part about CUDA, all of this is actually happening underneath. So you should be aware. Even dnums of 3, there is a CUDA mem copy happening. Right? Because you want to copy the memory from device to host, which can be printed on the CPU. There is a transform function which I can do that from source to end and another source. So using these two, I'm applying some sort of a binary operation. I'm applying an add on the corresponding elements of these and store it at the destination address. Right? So all of this is possible using thrust. So that becomes really easy for you to write the code for, and I'll show you one example. Yeah, so some other functions that are provided using in thrust are find, where you can search for an element. You can search for using a predicate. Again, copy and copy with respect to certain predicate. Then equal, whether two elements, whether the two aggregates are equal or not. Minimum element, maximum element. You can also merge two sequences. You can sort them. You can also do a reduction. Reduction I'll explain a little bit as we go along. And then the mother of all transformations is called transform, which also we are going to quickly look at. Okay. So thrust algorithms have this host and device dual implementation. So you can imagine that there is underscore underscore host, underscore underscore device. Those kinds of functions are also going to be there as part of thrust library. Okay, so let's look at one specific example, and we are going to make use of all these headers. So allocate 3 device vectors with 10 elements each. Let's say x, y, and z, which I am going to declare as device vector x, device vector y, device vector z, and I specify the initial size. I can initialize x to 0, 1, 2, 3, and you know which function to use. That is called a sequence. So I can use that to create the variable, create the sequence. Now I can do y equal to minus x, right? So these are the kind of operations that you will see in your setup, in your computational engineering, where you want to do y equal to minus x or some large computation, right? Y equal to ax plus b, something like that. So let's say that minus x I want to do, that I can do directly using a transform function, which does that I am going to take x dot begin to x dot end, which are 0, 1, 2, 3, 4. Or whatever be the original array, and I'm going to write it to y dot begin using this negate as the operation. This negate is already provided in thrust, which you can use, but there could be some functionality which is not provided in thrust. How do you do that? For that, we will have to write our own functor. We'll write that in a minute. I can fill another vector with all 2's. Why? Because I want to perform some processing, like I was saying, ax plus b. So I can use a fill function, or I can create a kernel, right? To which I can create an array in which you can do initialization a of thread id x dot x equal to 2, right? Like that you can do. Or you can use this thrust fill function, which initializes all these 10 elements to 2. Now I can do x mod 2. Right? So that I can use again using a transform. There I am passing the parameters as x dot begin to x dot end, that is 1. Then z dot begin. What is z? Z contains all 2's. That is the reason why we initialize those, because I want to do a mod. Note that mod is a binary operator. So it requires these 2 arguments, x dot begin and z dot begin. In contrast, negate was a unary operator, and therefore it just required x. Y is required as the destination, which is required in both the cases. So that is the reason why we have this requires 4 parameters, whereas this requires 5 parameters. So because this is a binary operator. So x mod 2 I can do using this z. Can I not pass 2 as a parameter here? Unfortunately, that doesn't happen. That doesn't work because its parameter needs to be an iterator. So therefore, we have initialized this z with all 2's. And then the modulus happens with the corresponding element of x, corresponding element of z, and storing it at the corresponding place inside y. So that is what is the transform. Replace all the ones in y with 10's, that I can do with a function called replace all the ones in from y dot begin to y dot end by 10. And I can also print y. I can use a for loop, but there is another interesting way to do that, which you can copy the elements from the device vector to ostream operator. What is ostream? That is the cout operator, cout object. So you can actually copy from y dot begin to y dot end onto this particular, let's say, stream, right, using /n as a delimiter. So that is another way in which you can do, but essentially it is printing the elements. Any questions on this code? All these codes are available on the web page. I strongly recommend you guys to try it out. Okay, so when you have user-defined functionality, for example, I have this sigma x plus y, that is usual the operation that is required in linear algebra. What I want to do is to have x and y as the input device vectors and result as the output vector, and let's say that I have populated x and y, right, via some mechanism. Now I want to compute the ax plus y sigma of all of that, right? So one of the ways in which I can do is that I can do a transform where I start from the x variable, the vector, then the y vector, and then I'm going to write some processing of that into the result. But now the transformation that I want to do, I can do multiplication and plus using thrust functions, that is okay. But if I want to do something of my own, I can define sigma ax plus y, that is called saxp, right? So sigma or summation ax plus y, and a is the coefficient that I'm passing as a parameter, right? So what does this do? This creates a temporary object of type saxp. Saxp is not a function, it is called as a functor, which means that it is actually a structure or an object or a class. How do I do that? Well, I just define it of that type as a structure or a class in CUDA, and I am going to create an operator, which is the function operator, the opening and closing parenthesis. So this is the operator which we are overloading, to which two parameters get passed. One is coming from this x, another is coming from this y, and this gets repeatedly called by the transform function. Okay, so you can print these values and you can write arbitrary piece of code inside this functor. In general, in this case, I am just going to use ax plus y. Right? That is the operation that I want to do for each individual element. So this operator is going to get invoked as many times as the length of x and length of y. Okay. So what is missing? The missing part is, what is this a? Well, that a is a constant which we want to define. But then what is this underscore of a? Is it that inside the functor it becomes underscore? No. Underscore a is different parameter. A is different parameter. But since this is a class or a structure, by default it is going to get instantiated, and therefore it is going to get called, it is going to call a constructor. It is going to invoke a constructor. That constructor I am making use of to store inside a variable, a local variable inside the structure, which I am defining as underscore a, but you can define it as b. That b gets the value of the local parameter a, which is passed as a parameter here, which is same as this one. So I store that from the constructor, and then when the function gets called, I make use of that stored variable as part of the computation. Okay, so that is how this linking happens, and it's a beautiful usage of C++. Is this similar to lambda functions in Python? Not really. There are lambda functions in C++ also. Lambda functions turn out to be slightly different than this one. This is a little more concrete. It doesn't create an abstraction yet. Yeah, you can write lambda function in a different way. This is not lambda function. This is just functors. Okay, so that is what I define as constant float underscore of a as part of the class. So in C++, struct and class are interchangeable, except that struct has default public visibility, whereas class has default private visibility. Okay, some of you will find it a little difficult, but digest it later, and if there are any questions, please feel free to ask me. But as of now, are there any further questions? All right. So you can try this exercise using similar thrust functions. Let me talk about a little bit about reduction. Reduction means that you have large number of values and you want to reduce it to a few values. Typically this few is 1. For example, if I have large set of numbers and I want to sum them, that sum is one variable. Or I want to create a product of all of them, that is a single, that is a reduction. Or I am given an array and I want to find the maximum element in it, that is a reduction. Right? So all of these are different ways in which you can do reduction. And this reduction turns out to be an important concept in parallel programming, and Thrust also supports that. For example, I can just do, let's say I have some host vector and device vector. I can just do a reduce on begin and end of this host vector or device vector, and I get sum of all the elements, because sum is the default operation for reduction. And at that sum, I can return as a parameter directly on the host side. So this turns out to be very easy for you to do rather than writing a kernel. Right? And we don't have to worry about the number of blocks, how to synchronize, whether to use atomics, etc. All of that is kind of hidden from. So the meaning of this is that reduce takes multiple parameters. It can take 2 also. So these are called as polymorphism. You can have the same function name, but you can have different number of parameters in C++. So because of this, there are multiple functions supported. One has 2 parameter support, another one contains 4, where this is the base value, and that is the operation that you want to perform. And here, this plus operation could be your own, the way exactly we did for the functors. Right? For example, if I want to implement my own count function using reduction, where I want to count the number of occurrences of an element inside a vector, I can do it this way, where I can call a thrust reduce on a vector dot begin dot end. I start from 0 because that is the default value initially. I call my count of 5, where 5 is the element that I want to search inside a vector. And I just print that result because that is the return value. So how do I write the functor? Well, I can say that my count is going to be a class or a structure which has a constructor which takes this 5 as a parameter, that is integer, which I store inside my local variable. Here also I am calling it as underscore, but you can give it some other name. And then there is a host device operator, which, so host device meaning it is possible to be called from host vector also, from device vector also. Right? So in this case, we just require it to be a host function, but it's a good practice to do it that way. And then there are 2 arguments that it is receiving. What are those 2 arguments? It's not the 2 elements of the vector. It's the previous value of what this reduction was getting called with. What was the original count? That is the y value. And the current element of that vector, that is x. So, the other way around. X is colon functionality in C. And that finally goes on incrementing the value of this result of this reduce, and you get the correct value at the end of this invocation. So it's a little complicated for some of you, I know, but try this out and you'll be able to get it. Any questions on this? Okay. There is also prefix sum or scan, as they call it, which is a cumulative sum of the array elements, which can be useful in certain applications. For example, I can say that if this is my original array and I want cumulative sum, then cumulative sum is going to start with 1, then 1 plus 0, then 1 plus 0 plus 2, 1 plus 0 plus 2 plus 2, like that. So that is 1, 1 plus 0, 1 plus 0 plus 2, and so on. Right? So that is called as inclusive scan. Exclusive scan always starts with some base element like 0, and then the rest of the elements get shifted by 1. Okay, so that is called as an exclusive scan, and the last element is missed out in the exclusive scan compared to inclusive scan. Right? So that can be useful in case you want to do some sort of histogramming, or you want to find out sometimes where the element should be inserted into let's say a concurrent array and so on. So this can be useful in some applications. but I'll skip this, and actually I'll skip streams and events because that is going to be less used, but some of you might actually be using multi-GPU processing. So let me just go to multi-GPU part. I'll skip this streams and events, which is again an interesting topic, but I'll skip this in the interest of time. Okay, let me spend some little bit of time on multi-GPU processing. So first of all, why multi-GPU? Well, having you can do multiple CPU GPU backend kind of handshakes, right? So if you have single GPU, you can transfer the data, get the data back, but then sometimes your data might be very large, which might not fit into single GPU, and therefore using multiple GPUs is one part. The second part is parallelism. If multiple GPUs can run concurrently, then you can get the same job done faster, right? So therefore, it makes sense to use multi-GPU in certain situations. So when you have multiple GPUs, typically you will have a CPU which might be connected to multiple GPU backends. And you might be able to make use of them in several situations. For example, those of you who are from IIT Madras, we have this Aqua cluster as the central computing repository. There, each node has 2 GPUs installed on them. So you might be able to make use, learn this there. Okay. So how do you do multiple devices? Well, these are always numbered from 0, 1, 2, right? Irrespective of the make of the GPU, etc. So for example, you can have a Volta GPU as well as a Kepler GPU as well as probably a Titan GPU on the same machine, but they are always numbered 0, 1, 2, right? So that can be very useful, and you just need to remember this particular function CUDA set device of I, and you select that particular device. So the rest of the operations are going to happen directly on that device. For example, I can do CUDA set device 0, which is the default, right? If you have multiple GPUs and you are running your code without any CUDA set device, it will always run with device 0. Okay, and I run kernel 1, then I do CUDA mem copy. So both this kernel and CUDA mem copy are going to refer to device 0, that is GPU 0. Then I can do CUDA set device 1, and the kernel 2 and CUDA mem copy will refer to that particular 1th device. Okay. Any questions on this? Okay, then I have a question for you. So there is something wrong with this code from parallelization perspective. Can you tell me what that is?
CUDA set device 0 and device 1 are like they finish the tasks one after the other. So
Right.
maybe
That's right. So what Sandeep said is correct, that there is a sequential processing happening, right? Ideally, the device 0 and device 1, you want this K1 and CUDA mem copy should happen in parallel. K1, K2 and CUDA mem copy should happen in parallel. So how do you do that? Any suggestions? What is stopping it from doing this processing in parallel?
something similar to CUDA device synchronization we need to use for CUDA devices.
No. So no, currently what is, I'm telling you that currently the 2 devices are used one after the other, not simultaneously. Why is that happening?
Memcopy inside has synchronization.
Right. Memcopy is blocking for the CPU. CUDA memcopy is blocking for the CPU, and therefore, if you use this, the CPU is going to wait till CUDA memcopy is over. It will not do CUDA set device 1. That means that kernel 1 is going to get over, then CUDA memcopy will get over, and then the CPU is going to execute CUDA set device. This can be taken care of using the asynchronous version of CUDA memcopy, and then similar to kernel launch. So the CPU is going to just launch the kernel, come back, and kernel is going to get executed at some point. Similarly, it will just push the CUDA memcopy into a queue, so it will get launched and CPU will come back, and it will do CUDA set device 1. It will do a kernel launch, and then it will do again CUDA memcopy async. This async could be last CUDA memcopy could actually be CUDA memcopy, whether async or not. But typically you will not have such a code. Typically this code will be inside the loop because you want your code to scale with number of GPUs installed. Therefore it will be inside a loop, and therefore you will use CUDA memcopy async. For example, to know the number of devices in your code, you can just write a C++ program like this. Essentially this is going to be part of the device query that you have in your CUDA SDK. So you know what you get the device count, and you can also get device properties. That is, what is the compute capability it supports. There are other properties also which you can print using this. So right. So kernel launches are made on the currently set device as well as the memcopy calls. Yeah, streams and events we didn't study, so that I'll have to skip. So I think I'll probably stop here. Let me just yeah. So memcopy. Yeah, again this is related to streams, so I'll have to skip this part. Yeah, events also I'll have to skip. Yeah, there's an exercise using again events. This we won't be able to do. All right, so that comes to the end of the fourth lecture. So we did CUDA computation, memory synchronization, and we looked at two topics. One was related to thrust and functions. The second one was related to multiple GPUs. So once again, these are just the initial icebreakers, and there is a lot to be done in each of these. It's just that I would like you to spend time on these topics, whichever is applicable in your particular application that you are doing. And feel free to get back to me if you face any trouble. There are yeah, so next 2 weeks, Dr. Pradeep Ramachandran is going to talk a little more about generic programming on accelerators. So that is something which you will find useful in your applications as well. Hari says, is synchronization across devices possible? Yes, so you can do CUDA device synchronize across these. If you are talking about whether a thread which is running on one device and another thread running on another device, whether they can synchronize across each other?
Yes, sir.
Yes, so that is possible in a limited way. For example, if you do a host-alloc'ed memory with respect to different GPUs, you will be able to make some sort of communication from one GPU to another, but the CPU will have to intervene because we'll declare the host-alloc'ed memory with respect to one GPU and then host-alloc'ed memory with respect to another GPU, and then the CPU will have to intervene. If you want CPU to not intervene, there is something called as peer access across GPUs. That peer access can allow you to access other GPU's memory from your GPU device without involving the host. So that peer access can help you coordinate across two GPU threads. If that peer access is not enabled, then there is no other way than accessing via the CPU. The CPU is involved in this. Sandeep says, is there any book you would like to suggest for us for this course? Yeah, so there are some books now in the Indian market which are reasonable. I haven't really looked at them carefully to make a recommendation. But my strong recommendation is that you go through the slides. So I am going to share with you at the end of this course some of the slides that I teach at IIT Madras, which is a semester-long course. And also the videos some of you had shared last time, the link to the HPC Education YouTube channel, where we have this course already there. So those I would recommend going through, because the books might sometimes get a little bit of daunting. Suddenly we'll start seeing, okay, these are the 1D, 2D and 3D grids and so on. And you will get lost in .x, .y, .z, which is not really required. I mean, that you can learn later. It's not really required for learning CUDA programming as such. So therefore, I recommend that you go through the slides first, and then you go through any of the books that should be ordered. So I'll share
Sure.
the slides that I am sharing. Those are probably going to be little filtered version, but I'll share with you the course slides on the book.
Sir, I had a question regarding last class. So there was a program, a snippet you shared, which had parallelized finding a maximum number in array and using shared memory. So the question is, does it actually improve performance? Because at the end of the day, it has to go through every single element, and then if you use atomic write as well, does it actually improve performance?
No, it can actually degrade performance. So you are right. There will be cost involved in executing this atomic instruction, in executing this synchronization. So actually the performance will reduce. That is not the best way to do. We should use reduction actually on the GPU to improve performance. That reduction, unfortunately, we could not cover in our class. But yes, that can actually compete with what happens on the CPU beyond a certain array size. You are right.
Sir, theoretically, what's the maximum limit to which we can parallelize operation like finding a maximum number in array? Because you would have to go through every single element at one point to actually find out what's the maximum number. Right?
That is true. But what you can do is, okay, let me take a simple exercise. Let's say that you have a bunch of friends, I have a bunch of friends. Let's say each one of us has a bunch of friends, and we want to find out what is the highest age, or who is the, let's say, the most aged person amongst all these groups. It's going to be probably me, but let's say that we want to actually confirm that. Now, one of the ways in which this can be done is that, yes, we want to touch every person. We'll have to ask the age of every person. But you can do that in your group separately. I can do that separately in my group. Sandeep can do it in his group. Elakia can do in her group. And all of this can happen in parallel. Once this gets done, the maximum age from each group can actually be checked. And the number of such elements is going to be much smaller, equal to the number of groups compared to the original number of people. So this is how the reduction works. And that can give you parallelism. So in the degenerate case, we have just two elements. We find the max of these two, these two, these two, these two. So starting from n, we come to n by 2 elements. Then from n by 2, we go to n by 4, n by 8, like that, all the way up to 1. So we require this log n number of steps to reach that 1. So yes, that log n number of steps are required, but if you have enough parallelism, this can actually give you benefits beyond certain value of n on the GPU.
Yes, sir. Understood.
There are some questions. Sandeep says, how did you learn for the first time? Am I allowed to ask this question? Yes, you are allowed to ask this question. I actually learned it on the job. There weren't good books at that time. I learned it around 10 years ago, GPU programming, and I have been doing it since then. I also had the, I should say, very nice guidance from Professor Martin Bircher from Texas State University, who was my mentor at that time. At that time, I was doing my postdoc, and I was looking at GPUs for the first time. In fact, parallel programming for the first time. So we didn't have good books. So my suggestion is that you have to get your hands dirty. There is no escape from there. But yes, a good book can help you. But my recommendation is go through my slides and then go through a book. I think that will be more helpful. Shiva says, if one GPU is filled by the memory, then how to use multi-GPU in that case? So you do a CUDA set device 0, you do CUDA malloc, CUDA memcopy on that. Once it gets filled, then you do CUDA set device 1 and start doing CUDA malloc there. That's it. So, but yes, you will need to know whether your memory is full. So typically the CUDA malloc, if you have it inside a loop, you can check the return value, whether that pointer, that ampersand of array that you are passing, whether that is null. Right? Similar to malloc, CUDA malloc will also set it to null if the CUDA malloc has failed, if it doesn't have enough memory available. If that happens, then you go to a CUDA set device 1 and do that. That is one way in which that can be done. Alternatively, you can just say that, okay, this is the overall memory, and I'm going to divide it equally across the number of devices that I have available. That is another way. Koti says how to handle corruption of data while copying from CPU to GPU and vice versa. What do you mean by corruption of data? Why will it happen? I didn't understand. You mean, are you getting into security aspect that somebody is doing side channel attack or something? By default, if your code is correct, there should not be any corruption of data. Right. So, I mean, as long as your program is all right, properly written, there should not be any problem. Pranod has given a link to learn CUDA programming, beginner's guide to GPU programming in parallel computing with CUDA 10.x and C++. Got this one, but not able to look into it yet. There are examples in C++, both solved and unsolved. I guess for every chapter, will this be sufficient after the slides? I think that should be good. I think that should be good. I haven't looked at it, but I suppose. Oh, this is Bharat's book. Oh, I see. I see. Bharat himself is from NVIDIA. So I suppose the book should be good.
Hello, sir.
Yeah. Go ahead. Yeah.
Yeah, my question regarding suppose 2 or 3 modules were running in the project which are using the GPUs. There is a threats on priority basis. It is coming to the system, and in that case, suppose 2 modules priority is same. In that, maybe can I expect any corruption in the data while copying from CPU to GPU or GPU to CPU?
No, no, nothing of that sort should happen.
How far we confident about that one? Like where it handles internally, it is handled by any functionality.
Okay, so if you are writing to the same array,
Okay.
then there will be corruption.
Mm-hmm.
If you are writing to 2 different arrays, there is no problem.
Yeah, yeah.
Right. So the only part which is going to be common is going to be this host side processing, because the GPUs are 2 independent entities, right? So 2 GPUs, assuming in this case, they will have their own connections, PCI Express buses. So they're also, it's all independent. The only thing that is common is this host. So whatever we are doing on the host, that can lead to some corruption, but that will be programmer's mistake.
Okay.
It will not be the hardware mistake. The hardware is all clean. Don't worry about that. The hardware will not cause an issue, except in case of the security aspects where there is some sort of an attack happening explicitly to garble the data. Don't worry about it.
Okay. Yeah. Okay, sir. Thank you so much.
Okay. Shiva says then we need to transfer data across multiple GPUs. Yes, that is true. That is true. So have data on the CPU and you want to transfer some data to first GPU and then some other data to another GPU and some other data to yet another GPU. That is possible. But was your suggestion situation a little different?
Sir, I have a question.
Yeah, sure. Go ahead.
Sir, if I am allocating a matrix on device 1 and another matrix some B on device 2, if I want to add those 2 matrices, then I should first transfer 2 to again 1, no, sir. Then again I have to allocate memory on 1 also, right?
Yes. So there are 2 ways in which this can be handled, or rather 3 ways I should say. One is, yes, you allocate memory on one device for the other matrix, you copy the whole matrix, and then do the processing, and then copy back the result. That is one way. The second way is, so that is the normal way. The second way is where the peer access comes into picture. So the first method, which I just explained, that requires the host, because the CUDA malloc needs to be done from the host side. So the host decides, okay, I'm allocating this A here, B on the other GPU. Let me allocate B's copy also on the device 1. Let me do CUDA mem copy, and then I'll invoke the kernel to do the matrix multiplication or whatever. The other way is that using peer access, GPU 2 can directly access the matrix from GPU 1 without involving the host. Right, so that can give you some advantage. Then, of course, internally there is a copying happening between the 2 devices, but that is kind of hidden from you.
Okay.
right? So I did cover this part, peer access. When I share the slides, the final slides that we study in the at IITM, there I'll have some slides on peer access, so you might want to go through that. That might be helpful to you.
Sir,
Sir, is peer access better than unified memory? Means
yeah, actually, underneath it uses the unified memory.
okay.
Correct.
Sir, I actually tried using atomic instructions on volatile memory, but it didn't actually allow me to do that. Is there any specific reason why it's not allowed?
Yeah, so I think it's just the type. You got a compile time error, is it?
Yes, sir. Yeah.
Yeah, it's just the type mismatch. You'll have to typecast it to, let's say, int star. Just without that volatile, it will work.
Okay. Yeah. Thank you.
Okay. Any other concerns, questions from anyone? Yeah, by the way, you guys are not using the group effectively, right? So you should ask questions on the group where your friends as well as me can answer the questions. So feel free to do that. Not only about assignments, but also about what we study in the class. All right, so I'm going to stop here. I don't